All right, so now that we've talked about the concept of dimension, let's put it all together. We're going to look at some vector spaces, some subspaces really of vector spaces actually, and we're going to find the basis for and dimension of those things. Again, the easy part is the dimension. The hard part is the basis, right? Once we find a basis, we just count up the number of vectors in the basis, and we're done. That's the dimension. So dimension's easy. Basis takes a little more work. Okay, we're going to take a look at this problem, find the basis and dimension of the solution space of the following homogeneous system. If you remember in section 4.2 on subspaces at the end, we talked about the fact that the solution space to any homogeneous system is a subspace. In this case, it's a subspace of 6 space, right? Because what are the solutions to this system? What are they? They are ordered 6 tuples. Do you see we have 6 unknowns in this system? All right, they're ordered 6 tuples. So it's the subspace for this, or the solution space rather for the system is a subspace of 6 space. Also, we've called that this is also really the kernel for the matrix transformation. If I look at the matrix transformation, whose standard matrix is the coefficient matrix for this system, then what is the same thing is then that this solution space is the kernel of that matrix transformation. Okay, so either way we can now do this. How would we find a basis for this system? Answer: solve the system. What's the solution space? What's the solution to the system? This goes back to day 1. Almost, right? The very beginning of the course. How do we solve a system of linear equations? Now notice we have 4 equations and 6 unknowns, so this is not a square system. So I can't use any relationships about invertible matrices and so on and so forth. But I have my good old way to do it, and that is what? Form my augmented matrix and do Gaussian elimination to put it in a row echelon form. In fact, I'll do Gauss-Jordan elimination and put it in reduced row echelon form. Let me get my augmented matrix. Now there's a lot of things going on here. Notice we've got 4 equations and we have 6 unknowns. That means we're going to have 4 rows and 7 columns, right? 6 for the unknowns and 1 for the constants, which of course are all 0. And so there's a lot of numbers you're copying down. What's the number one problem that we run into? A lot of times just copying down correctly. So it's worth your while to double check right after you've entered everything, and double check that you've entered in correctly all these coefficients here. Okay. All right. So now we're going to put this in reduced row echelon form. Again, we're going to use technology to do that, but we remember the process, right, of getting, leading one here, zeros beneath it, leading one next, zeros beneath it all the way down, and then getting the zeros above the leading one. So we went through that algorithm. Okay, so here is the reduced row echelon form. Make sure you confirm this. Okay, so there's the solution. So remember, what we've got here. This is the coefficients of x of 1, coefficients of x of 2, all the way down to what? Coefficients of x of 6 here, and these are our constants, right, which are still 0. And what we want to look at is leading ones, right? How many leading ones do we have? Well, let's see. The first non-zero entry in this row is a leading one. First non-zero entry in this row. First non-zero entry in this row is a leading one. No leading one anywhere else. So notice that x of 1, x of 3, and x of 5 are fixed variables. But x of 2 does not have a leading one, x of 4 doesn't have a leading one, and x of 6 doesn't have a leading one. So these are free variables. and they become what? Parameters, right? Notice this is a homogeneous system. We already knew that there was infinitely many solutions. If you remember, we proved previously that you have fewer equations than unknowns for a homogeneous system than there's infinitely many solutions. Remember, homogeneous systems are always consistent. Obviously, I can let all the variables be 0, and that's always a solution. But in this case, we have infinitely many solutions, including that trivial solution. So I'm going to assign parameters to these free variables. I'll let x of t be r, I'll let x of 4 be s, and I'll let x of 6 be t. All right. So how do we solve it? Let's get our first fixed variable here from the first equation and solve for it. So I've got 1x1 plus what? 2x2 plus 0x3 plus 3x4 plus 0x5 plus 5x6 equals what? 0. There's my first equation. And what am I going to do? I'm going to solve for my fixed variable. So I'm going to subtract 2x2, subtract 3x4, subtract 5x6 from both sides, and then I'm going to replace, right, x2 with r, x4 with s, and x6 with t. So I'll get x1 in terms of those parameters. So minus 2x2 is minus 2r, minus 3x4 is minus 3s, minus 5x6 is minus 5t. Right, there's my fixed variable x1 solved for. Now my second fixed variable is x sub 3. Let's solve for that. In this equation, I'll get x sub 3 plus 2x sub 4 equals 0. Right? So solve for x sub 3. A little bit easier. And this time, right, just subtract 2x sub 4. You get negative 2x sub 4 is what? S. And the last equation is what? This is 5x sub 5 plus 2x sub 6 equals 0. Sorry, I said 5x sub 5. 1x sub 5 plus 2x sub 6 equals 0. Negative 2x sub 6 is t. Okay, so now I have basically solved the system. I know what x1 is, x2, x3, x4, x5, x6. But here's what we want to do now. I want to write out my solution this way. It's an ordered six-tuple, right? Ordered six-tuple. What's x sub 1? I'm going to rewrite it negative 2r minus 3s minus 3t. X sub 2 is what? R. X sub 3 is negative 2s. X sub 4 is s. X sub 5 is negative 2t. And x sub 6 is t. Okay? Now, this is the solution, right? In other words, pick r, s, and t to be any real numbers you want, and you'll have a particular solution. There are infinitely many solutions. Now, what we're going to do in order to get the basis for this solution space is I am going to write this out, and instead of explain what I'm doing, I'm going to write it out and see if you understand what I'm doing here. So I'm going to look at r times this vector, negative 2, comma 1, comma 0, 0, 0, 0, plus s, negative 3, comma 0, comma negative 2, comma 1, comma 0, comma 0, plus t times negative 3, comma 0, comma 0, comma 0, comma negative 2, 1. All right. I don't know if you followed what I've just done here, but I will ask you this. If you scalar multiply this vector by r, this vector by s, and this vector by t, add the three together, does everyone see we get back to what we have right up here, right? I've just written this vector x as a linear combination of three new vectors, three new six-tuples. Okay? One for each parameter. And that's always going to be the case when we're solving these homogeneous systems. Now, what have we just done? We have every solution, every vector that is in the solution space to this system can be written what? As a linear combination of these three vectors. Every solution to our homogeneous system can be written as a linear combination of these three vectors. And therefore what? These three vectors span the space. They span the vector space. Okay, that's a good thing. Now think about a basis. What has to be true? They have to span the space. What's the other thing? They must be linearly independent. Are these three vectors linearly independent? They are. And let me explain why. Any one of these vectors cannot be written as a linear combination of the other two. So let's talk about it. This first vector here, this -2, 1, 0, 0, 0, 0, cannot be written as a linear combination of the other two. Do you see why? Do you see why this vector here cannot be written as a linear combination of the other two? Let me point out the culprit to you. Take a look at that right there. Look at that 1 in the second coordinate, the second position there. Is there any way to get a 1 here by taking a multiple of this vector, look at there, and this vector? Is there any way I'm going to get a 1 by taking a multiple of 0 and adding it to a multiple of 0? Not going to happen. Right? So this vector here cannot be written as a linear combination of these two. What about this vector? Can it be written as a linear combination of the other two? No. Do you see why? Well, for one thing, look at that guy. Look at that guy right there in the fourth position. It's a 1. Can I get a 1 by adding a multiple of this vector to this vector? No, not going to happen. Finally, this vector here, can it be written as a linear combination of the other two? Look at this 1 here. Am I going to be able to get the 1 by adding a multiple of this vector to this vector? Not going to happen. These vectors are linearly independent and they span the space. Therefore, they form a basis for the solution space. Before I write that down, let me just say, every time you do this process, what we just went through to determine if the vectors are linearly independent, you do not have to do, because you are always guaranteed to get these three vectors to be linearly independent if you put this in the reduced row echelon form. Okay, you're going to be guaranteed that these three vectors are linearly independent. In fact, that's true for any row echelon form, although it's not quite as clear as it is when it's in the reduced row echelon form. And the idea is these ones basically go back to where we had these leading ones, and look at all the other entries, right, in the columns. Remember, if you're in reduced form, all the other entries are zeros. Okay, so that's why it was easy to see this, but it's actually true for any row echelon form. But here's the point: when you do this process, these three vectors will always be linearly independent. So the answer is, what is the basis for? I should say, what is a basis? Very important here. It's the vectors. Don't include the parameters r, s, and t. Just the vectors. So it's this vector, right? This ordered sextuple. This vector. And this vector. And so what's the dimension? That's the easy part. Basis was hard. Dimension in one step. Count them. 1, 2, 3 vectors. It's the number of vectors. Again, this basis is not unique. Again, had I put this matrix up here in row echelon form, some slightly different row echelon form, we can get a different situation. And I can even take any scalar multiple of one of these vectors and replace it with that scalar multiple, that non-zero scalar multiple, I should say, and we will have another basis. So there's infinitely many bases, but all of them will have how many vectors? 3. All of them will have 3 vectors. Okay. So there's an illustration. Let's take a look now one more idea, and then we're going to play a little game. Here's an important theorem that we basically saw and talked about a couple lectures ago. So if V is a finite dimensional vector space with the dimension n, so now we can talk about this because we've talked about dimension. Let S be any set of n vectors in V. Then S is a basis for V if and only if S spans V or is linearly independent. Or. I thought we were a basis if it was both spanning and linearly independent. Well, here's the thing. If you know the dimension, okay, and if you go back and look, we did an example proving three vectors formed a basis for three space. Go back and look at that example in the previous video on basis. And the two questions we answered were that it was linearly independent and it spanned the space. But in both of those questions boiled down to the same issue. We were looking at a 3x3 matrix, and basically the question was the determinant not equal to 0? Was that matrix invertible, right? And that said yet that caused both of those questions to be yes at the same time. And that's really at the heart of what's happening here. And so what happens if you know the dimension of the vector space and you have that number of vectors in the set? You actually only need to check one of the two conditions and the other one automatically follows. So both conditions will be true if only one is. But that's only if you know the dimension. If you have a set of vectors in a vector space and you don't know the dimension of the vector space, well, you're going to have to check both. Okay, you're going to have to check both. But if we know the dimension and we have that many, so if I'm dealing with a set of three vectors in three space, are they a basis for three space? Well, technically we would only have to check one thing, like linear independence. If we show they're linearly independent, then they must obviously span the space. Okay, I'm not going to prove this theorem, but we kind of, in a way, we're at the heart of the proof in that example we worked out in the lecture on basis. Now, one more thing about subspaces and dimension. If W is a subspace of the finite dimensional space V, then W is finite dimensional. The dimension of W is less than the dimension of V, and W equals V if and only if the dimension of W equals the dimension of V. And we can think of this in terms of from familiar territory. What if V was equal to 3 space? Then you should know, I hope by now, what are the possible subspaces of 3 space. There are 4 possibilities. Number 1, all of 3 space. Number 2, planes through the origin. Number 3, lines through the origin. Number 4, the 0 subspace. So if you look at each of those, let's say lines through the origin. Let's suppose we have a line through the origin, which is a subspace of 3 space. So if W is a line through the origin, then W is finite dimensional. What is the dimension of a line passing through the origin? Well, what would be a basis for any line? If we have a line passing through the origin in 3 space, right? Then what is a, I suppose this is our coordinate system here, because we got our X, Y, and Z, and right there's the origin, so our line is passing right through the origin. Well, any vector on this line that's non-zero, let's say this red vector here, this one red vector spans the entire line, because any scalar multiple, if I multiply by something bigger, I move this way, something smaller, I move this way. If I multiply by a negative, right, scalar, I move this way, and it stretches or condenses that vector. So this red vector spans the entire line, and it's non-zero. So this one vector would be a basis for that. Therefore, the dimension is what? 1. A line is one-dimensional. Hey, surprise, surprise, right? So notice it says what, right? 3 space is dimension 3, so the dimension of W is 1, so less than or equal to dimension 3, right? Now, what if W equals V? Well, that's true if and only if their dimensions are equal. So remember, 3 space is a subspace of itself. In that case, if W is 3 space, its dimension is 3. And that's the only thing. But the important part is any subspace will always have a dimension that is less than or equal to the dimension of the space. So 6 space, right? We can have subspaces that are dimension what? 0, which is the 0 subspace, 1, 2, 3, 4, 5, and 6, which would be all of 6 space. All right, so we're going to put together this idea here, as well as from the last video we talked about these important things. Remember, if we have a vector space with dimension n, if there are more than n vectors, then that set is linearly dependent. If there's fewer than n vectors, then that set does not span the space. All right, let's put these ideas all together and everything that we've talked about so far. We play this game called never possible, might be possible, or it must be true. So we're going to place the number in the blank next to each statement. 1 means the statement is never possible, 2 means it might be possible, and 3 means it must be true. All right, the vectors v1, v2, v3, and the 0 vector form a basis for 4 space. Okay. We might say 4 space, hey, that's dimension 4, and count them, I've got 1, 2, 3, 4 vectors, so yeah. Not so fast, my friend. Look at that, 0 vector, what's that mean? This set must be what? Linearly dependent. Can a basis be formed from a linearly dependent set of vectors? No, it cannot. So this is 1, never possible. What about this? The vectors v1, v2, v3, v4 are linearly independent vectors in 4 space. Well, what about that? You might say, well, there's 4 vectors and we're in 4 space, they must be linearly independent. Well, they could be, but notice any one of these vectors could be the 0 vector. I didn't say anything about these vectors, and in that case, of course, the vectors are linearly dependent. V1 could be one vector that's non-zero. V2, V3, and V4 can all be scalar multiples of V1. I mean, we might not have the 0 vector in here, and they're still linearly dependent. So this might be possible. We can certainly have linearly independent vectors, but what about V1, V2, V3? 3 vectors in 4 space. Well, same thing again. Again, these vectors could be linearly independent, but again, any one of them could be the 0 vector, or one can be a linear combination of the other 2. We don't know. So 2 again. What about this? 5 vectors are linearly dependent. Notice I changed it from independent to dependent in 4 space. Well, here's where that theorem comes in. Since I have more vectors, what's the dimension of 4 space? 4, right? If I have more vectors, 5, then the dimension of the vector space 4, then the vectors must be linearly dependent. This must be true. This must be true. How about the 4 vectors here spanning 4 space? Well, any basis for 4 space must have 4 vectors, and any basis must span the space. So certainly that's true. But again, we could have all these vectors being scalar multiples of v1, v2, v3, v4 could all be scalar multiples of v1. In that case, they would not span all of 4 space. And so this might be possible. These 3 vectors span 4 space. We'll go back to that theorem we looked at in the last video. If you have fewer than the dimension vectors, the dimension of 4 space is 4. If we have fewer than 4 vectors, they cannot span the space. So this is never possible. What if you have more vectors than the dimension of the space? Can they span the space? You betcha they can. They can. But they may not as well. Again, I could have v2 being a scalar multiple of v1, v3 being a scalar multiple of v1, and so on. And so again, this might be possible. Okay, but you can have it. You can have, you know, a basis for 4 space consists of 4 vectors. So if, say, the first 4, suppose they formed a basis for 4 space, it doesn't matter what the 5th vector is. We're spanning the space regardless, right? I mean, I could take the linear combination of the first 4 and then just 0 times the last one if I have to. So again, this could span or it may not span. If there's fewer than the dimension, they cannot span. If there's more vectors than the dimension, the only thing we know is what they're linearly dependent. Okay, Now, the linearly independent vectors P1, P2, and P3 span P2. What's the dimension of P2? You remember the dimension of P2? It's 3. Right? Degree 2 or less polynomials have what? X terms, x squared terms, and constant terms. So there's a dimension of 3. Okay, you say, well, yeah, we have to have 3 vectors to form a basis for 2 space, but we don't know, right? We don't know whether or not they span. Well, not so fast. Since we know the dimension, and we have 1, 2, 3 vectors here, and we know what? That they are linearly independent. That's something that we're told is true. Well, what's true? Remember this theorem we just looked at. If they're linearly independent, right, we only need to check one of these 2 conditions for a basis. That they are a basis if and only if this is true or this is true. And this is true. They're linearly independent. So they must be a basis. And therefore, since they're a basis, both of these things are true. Okay, so again, essentially this theorem is saying, if we know the dimension and we have that many vectors in the set, and we know one of these 2 things is true, then the other thing is also true, and they form a basis. So the bottom line is, this must be true. The dimension of the subspace W of M34 is 14. That has to do with the little theorem we were looking at up here just a minute ago. Remember, the dimension of any subspace must be less than or equal to the dimension of the vector space that it's a subset of. What's the dimension of M34? You remember that? 3 times 4, 12. 14 is greater than 12. This is never possible. Any subspace of M34 must have dimension what? 12 or less. Must have dimension 12 or less. Okay, so those are a little tricky. I know you want to spend some time thinking about those ideas, and I will have more examples of those like on the review for the test, and you'll see them in the homework in the book. So please be thinking about those. Look at those in the true-false as well. All right, finish with 2 examples. Let's give the basis for and find the dimension of the following vector spaces. So first of all, the subspace of 3 space described by this equation. Now some of you recognize and know what's going on because 3 space we can think of geometrically. What geometric object do we have right here? Do you know? We'll come back to that. You should know if you've had Calc 3 for sure. Okay? Here's what I'm going to do. I'm going to think of it from linear algebra perspective. I have a system of linear equations. You say, what? I have a system of linear equations. I have one equation in 3 unknowns. All right, 1 equation and 3 unknowns. And, you know, I'm not going to put it in reduced echelon form. I can do that in one, real quick. But I'm simply going to solve for one of my variables, and the easy one to solve for is what? I'm going to solve for z, right? Z is equal to negative 5x plus 2y, right? And so in a sense, z is the fixed variable. X and y are my free variables. So I'm going to let x equal a parameter r, and I'm going to let y equal the parameter t. So that means any ordered triple, right, any vector in 3 space, right, that satisfies this equation must be of the following form. X is what? R. Y is what? T. Z is what? Negative 5x, which is r, plus 2y, which is t. Right? So every vector that is makes this equation true in 3 space must be of this form. So what do we do now? Do you remember? We rewrite it this way. See if this makes sense. R times 1, 0, negative 5, plus t times 0, 1, 2. Does everyone see how I got that, right? In other words, this vector can be written as a linear combination of these 2 vectors. So these 2 vectors span, right, this space, this subspace, and they're clearly linearly independent, right? They're clearly not scalar multiples of each other, because there's only two. And so there it is, the basis, or a basis again, not the only one, but this is a basis. And this is what I'm thinking you will do when I'm asking this question, right? Is these two vectors. And what's the dimension? That's easy. Count up the vectors. 1, 2. What kind of geometric object is this now? It's two-dimensional. What is it? This is the equation of a plane passing through the origin, right? It's spanned by two vectors, right? So if you think about it, in the plane, if we're looking in the plane, right, if I have two vectors, think of my pens as being two vectors, right? And as long as they're not scalar multiples of each other, I can take any linear combination of these two vectors. I can take, this green vector plus this red vector, right? It's kind of hard to see that, right? And I'll create vectors in the plane, any scalar multiple of them, right? So these two vectors span all of this subspace, which geometrically is a plane passing through the origin. What about the vector space for all n by n diagonal matrices? Remember diagonal matrices, n by n, what would it look like? Let me do it in general. The main diagonal entries can be any real number. So I'm going to say the first row, first column entry is D1. Second row, second column entry is D2. Right? And so on, all the way to the last row, last column entry, which would be what? D sub what? N, because it's n by n. Right? What has to be true? Any entry off the main diagonal has to be what for diagonal matrices? It has to be 0, right? So I've got zeros everywhere else, right? Zeros everywhere else, just along the main diagonal, right? So, can you think of a basis for this? Can you think of a set of n by n matrices that spans this vector space? We've done it before. What are we going to do? First vector in that basis will be the n by n matrix with a 1 here and zeros everywhere else. Right? The second matrix will be what? A 1 in the second row, second column, zeros everywhere else. I'll just put 0, 0, 0 everywhere else. Right? And then lastly, what? Zeros everywhere but this last row, last column entry. So basically, right, because each of these diagonal entries, how many are there? There's n of them. Each one can be distinct from the others. And so I can create this matrix by doing what? D1 scalar multiplied times this matrix, plus what? D2 times this matrix, plus D3 times the next one, all the way down to plus what? Dn times this one. And that gives me our arbitrary n by n diagonal matrix. Well, how many matrices do we have in this list? There are n of them, right? Because the 1 just moves down this main diagonal going through all n locations. So the dimension is n. Okay, so you'll need to play around with this in section 4.5 in the book. Look at the examples. There's other cases where you want to try and find a basis and dimension for the given vector space. So don't forget Zoom meetings. I'll be glad to look at examples that you're having trouble with in the textbook. So please come and ask questions. All right, so we're going to the next set of lecture videos. We're going to start talking about the fundamental subspaces of a matrix. And we're already familiar with one of them very much, and the other two we will describe as well. And then we'll look at properties and finish out talking about those dimensions, basis for and dimensions for those subspaces.